Hello everyone, this is Professor Roman. Let's continue the field theory lectures. A group G is said to be realizable over a field F if there is a field extension, Fe, whose Galois group is the group G. Another way to say this, instead of realizable, is realizable as a Galois group. Now, since any finite group of order n is isomorphic to a subgroup of Sn, this is Galois' theorem, we do have the following. Let F be a field, every finite group is realizable over some extension of F. So suppose G is a group of order n, let T1 through Tn be independent variables over F, and let S1 through Sn be the elementary symmetric polynomials in the Ti's. Then this extension that we have discussed earlier is Galois, and its Galois group is isomorphic to Sn. And by Galois' theorem, G is isomorphic to a subgroup, H, of the Galois group. And since H is closed in the correspondence, everything is closed, H is in fact the Galois group of this field extension. The Galois group of the fixed field of H over K is H. So that's just almost an immediate consequence of the fact that this extension has Galois group Sn and Galois' theorem. It's going to get worse before it gets better. It's a major unsolved problem in field theory to determine which finite groups are realizable over the rational number field. It can be shown that any finite abelian group is realizable over Q. And it's also true that the symmetric group Sn is realizable over Q. But the proof is quite difficult, and so we're going to do the proof only when n is p prime. And even this case, as you're about to see, is a little, shall we say, testy. We're going to begin by discussing a method for showing that the Galois group of a certain type of irreducible polynomial is a symmetric group. I'm calling the polynomial f of x because I've used p here for the prime, and I don't want to use p of x here. So let R be the complete root set of f of x in a splitting field. Now we know that G acts transitively on the root set. Also, just to be perfectly clear, I'm going to say that the Galois group G of f of x contains a certain permutation pi of the root set. But that's not really accurate. It's a little abuse of terminology. G contains automorphisms of the entire field, top field, in this case S. But when you restrict those automorphisms to R, you get permutations of R. So to say that the Galois group contains a permutation pi of the root set is really to say that G contains an automorphism whose restriction to the root set R is the permutation pi. But it's just so convenient to say G contains a permutation that that's what I'm going to do. But now you understand what I'm really saying. Define a binary relation on the root set by saying that two roots are equivalent, R is equivalent to S, if either R equals S or G contains this transposition, RS. This is clearly reflexive and symmetric. It's also transitive. For the reasons here, I'll let you think on that. And so it's an equivalence relation. We'll let square bracket R denote the equivalence class containing R. Okay, now, if G contains a transposition, it doesn't have to, but if it does, say RS, then for any sigma in G, we have sigma R, sigma S is equal to the transposition RS conjugated by sigma, which is in G. And so R is equivalent to S if and only if sigma R is equivalent to sigma S. The other direction you find by using sigma inverse here. It follows then that sigma applied to an equivalence class, say the one containing R, is equal to the equivalence class containing sigma R. And since sigma is injective, these two equivalence classes have the same size. But G acts transitively on R, the root set. So for any given root, all equivalence classes have this form for some sigma in G, and so all equivalence classes have the same size, say M. And M is at least 2 because this equivalence class that contains R, where we got the transposition from, also contains S. So this has size at least 2, so they all have size at least 2, which means that if there are E equivalence classes, since the equivalence classes form a partition of R, the size of R is M times E. Okay, so maybe you say, so what? Well, the so what is, if we assume that the size of R is prime, P, and also that G contains at least one transposition, which was what we've been doing, then M is bigger than or equal to 2. That goes here, but this is prime, so E has to be 1. In other words, there's only one equivalence class, which means that every pair of roots R and S are equivalent. Or, put another way, the transposition RS is in the Galois group. Well, the transpositions of a set generate the symmetric group on that set. So G has a complete set of generators for S sub R, which has size SP, which is the same, is isomorphic to SP. So, theorem, if f of x is an irreducible polynomial with a prime number of distinct roots in a splitting field, and if the Galois group of f contains a transposition on the root set, then G is isomorphic to the symmetric group SP. That's a lot of ifs, maybe, but one way to guarantee that a Galois group of a rational polynomial f of x contains a transposition is to assume that f of x has exactly 2 non-real roots, C and its complex conjugate C bar. Then the complete root set will look like this. R1 through Rn are real numbers, and the conjugation map on Q with the roots adjoined, that's a splitting field. This is S. The conjugation map is a ring embedding. It's injective and it preserves all the ring operations. So it's a ring embedding of QR into itself. But it maps the root set R, the generators, onto themselves because it permutes them. And so conjugation is an automorphism of Q with R adjoined. And it fixes Q. In fact, it fixes the real numbers. In other words, conjugation is in the Galois group. And so the Galois group contains the transposition that transposes Z and Z bar. All the other roots are fixed, so everything, it belongs to the Galois group. So, corollary, if f of x is a rational polynomial, is irreducible, of prime degree p, and has exactly two non-real roots, then the Galois group of f of x is isomorphic to SP. Here's a quick example. This rational polynomial of degree 5, Eisenstein's criterion shows that this is irreducible over Q, and it is separable because Q has characteristic 0, so it has 5 distinct roots. Take a quick sketch of the graph if you wish. You will see precisely 3 real roots, so its Galois group is isomorphic to S5. I believe we encountered this polynomial earlier in the course when we were talking about solvability by radicals. Okay, this corollary is just what we need to establish that SP is realizable over Q. What we need to do is show there exist polynomials, rational polynomials, that are irreducible and have any prime degree we wish, and they have precisely 2 non-real roots. This is a bit testy. Here's the theorem. For m equals 2 or m bigger than or equal to 3 odd, so this will pick up all the primes, there exists an irreducible polynomial r of x over q of degree m, such that r of x has precisely 2 non-real roots. Hence, for p prime, the symmetric group SP is realizable over Q. Here we go. You'll have to bear with me on this. Okay. For the case m equals 2, f of x equals x squared plus 1, we'll handle it. For m equals 3, g of x equals x cubed minus 2, we'll handle it. So we can assume m is at least 5, and it's odd. Let n be an even positive integer. Let k1 through km minus 2, so that's at least, m minus 2 is at least 3 now, so we got at least 3 of these, be distinct, positive, even integers. And let q of x be this polynomial, x squared plus n times the product of the linear polynomials with these roots. This polynomial, x squared, n is 2 here, x squared plus 2, and then the roots are 2, 4, 6, 8, 10, is shown in a graph here. And we're going to refer to this because we need to look at the properties of this polynomial. Q of x has exactly m minus 2 real roots, k1 through km minus 2, and exactly 2 non-real roots because n is positive. Unfortunately, it's not even close to irreducible over Q. Here is a prime factorization. Okay. So we're going to need to find a different polynomial by tweaking this one to get what we want. And for that, we make the following observations. Because m minus 2 is odd, q of x is negative when x is to the left of the first real root. It's positive when x is to the right of the first real root. And you can see that clearly here. Here's the first real root. Q of x is negative to the left. Here's the biggest real root. Q of x is positive. Here's the root here. Q of x is positive to the right of that. Okay, there are 1, 2, 3, 4, 5 real roots. This one. 1, 2, 3, 4, 5. Okay. Also, there are m minus 3 intervals on the x-axis lying between the real roots. What is m for this one? Well, m minus 2 is the number of roots here, and there are 1, 2, 3, 4, 5, so m minus 2 is 5, m is 7, m minus 3 is 4, and those are the 4 intervals I marked here. Okay, so there are m minus 3 intervals between the zeros. Now, the relative maxima and relative minima alternate within these intervals. Relative max, relative min, relative max, relative min. Specifically, every other interval, the ones with the odd index left endpoint, contain a maximum, the others contain a minimum. Now, if S is an odd integer, I'm interested in Q of S, and in particular its absolute value. Well, when you put S in here, you're going to get S squared plus N, and then you're going to get S minus K1 through S minus Km minus 2. But because S is an odd integer, at least one of these roots has distance at least 2 from S. So one of these will be at least equal to 2, these differences in absolute value. So the absolute value of Q of S is bigger than or equal to 2 times the absolute value of this first factor, which is strictly greater than 2. That tells us something about the relative maxima of Q of X. All of them are greater than 2. And so this polynomial R of X, which is Q of X minus 2, still has the same number of relative maxima, and therefore it has m minus 2 real roots. We drop this graph down by 2 units, we still have this positive relative maxima. Now, we want to choose a value of n in Q of X. So let me go back here. We want to choose a value of this n so that R of X has at least one non-real root, and then its complex conjugate will also be a non-real root. So we'll have 2 non-real roots and m minus 2 real roots. We know we have m minus 2 real roots. That was the whole point of this discussion. The question is, do we have m real roots? And we have to choose an n so that we do not. Then we'll have 2 non-real roots. So let the roots of R of X in the splitting field be alpha 1 through alpha m. R of X then, first of all, it's Q of X minus 2, but it's also the product of these linear factors in a splitting field. Equating coefficients of x to the m minus 1 and x to the m minus 2 gives us these 2 equations. And so the sum of the squares of the roots of R of X, do the algebra, we get this. So if n is sufficiently large, this will be negative. So not all the alpha i's can be real numbers, because then this would not be negative. So one of the alpha i's must be non-real. I'd like to know who thought of this proof. All we are left with now is showing that R of x is irreducible. We know it has exactly two non-real roots. Well, Eisenstein's criteria will help. So let's write Q of x. This is what it's defined by, and write it out as in the normal standard notation for a polynomial. In this product of the linear factors, each coefficient, except the leading one, which is equal to 1, is divisible by 2 because the ki's are even. So we can write this product as x to the m minus 2 plus twice x. This is pulling out an x here. We'll put the constant term over here. 2x f of x. F of x is some polynomial. Point is, it's divisible by x. And this is the constant term, the product of these guys. And since there are an odd number of them, is that an odd number? M is odd, yeah. So it's an odd, so there should be a minus sign here, I think. I have to double check that. Right. M is odd, and so m minus 2 is odd, so there's an odd number of negative signs. So yeah, so that should be negative sign. It's not going to make any difference. Multiplying by x squared minus n, so we get q of x. Looks like this. It's rather unpleasant, but that's what it is. Now, since n is even, by assumption, all the non-leading coefficients of q of x are even. This is even, this is even, n is even, n is even, n is even. Also, the constant term of q of x is divisible by 4 because n's divisible by 2 and at least one of the, and these are all even, and there is at least one of them. So R of x, which is q of x minus 2, is monic. All the leading, non-leading coefficients are divisible by 2, but the constant term is not divisible by 4. Okay. When we subtract 2 from here, this constant term is not divisible by 4 because this is, and therefore 2 would have to be divisible by 4. So R of x is irreducible. And the proof is complete.